И больше ничего? Трансляция не включается. О. Okay. So, last time we finished some notational preparations, and the outcome was that the union of conjugacy classes in Gn, union over n, is the set of partition valued functions underlined from phi to partitions. So phi is the multiplicative group of the algebraic closure of our finite field modulo the action of Frobenius, and it is the same as irreducible polynomials with leading coefficient 1, except for just polynomials. Okay. Well, it was sort of Jordan normal form. And this takes care of the eigenvalues, and the corresponding partition takes care of the Jordan. On the other hand, we also somehow numbered the union of irreducible classes, isomorphism class of representations. Well, we didn't quite do this, but at least we declared that the would-be characters will correspond to, will be equal to certain Schur-like functions, and those Schur-like functions will be numbered by something very similar, but rather partition valued functions lambda underlined from theta to p, and here theta is something dual, so it's L modulo Frobenius, and well, K algebraic closure of the multiplicative group was the union of Mn. Mn was the multiplicative group of K n, degree n algebraic extension, and then, well, it was a cyclic group, but we could take its dual group of characters, a dragon dual group, and then, well, those certainly form a direct system with respect to inclusions, but also an inverse system with respect to norm maps, and then those guys form the direct system as well. So L is the colimit of L. Okay. So, in a sense, there is some duality between parameterization of conjugacy classes and irreducible representations, and it's not bad because we are going to evaluate characters of irreducible representations of the conjugacy classes. But let me well, make some digression about this parameterization. Certainly, it's compatible with this grading by n, and well, maybe the slogan is that the isomorphism classes of irreducible representations of GL and K are numbered, maybe naturally numbered, by the conjugacy classes in the dual group. GL and I don't know how to say it, dual of K. Well, first of all, this dual is called Langland's dual. And well, it happens so that GL and Langland's dual is isomorphic, though non-canonically, to GLN itself. But it's sort of accidental coincidence. Now how what does it mean? Well, first of all, let's consider some baby case when our group G is not GLN, but is an abelian group, just a torus. Well, to some power. This. Well, or it could be maybe non-split torus. So it could be a multiplicative group over some finite extension or product thereof. So what really goes on, we take the algebraic closure, we take its multiplicative group, now we take its mth power, and then there is some action of Frobenius, but not necessarily the most standard one, which is the product of Frobeni in each factor, but well, some automorphism which plays the role of Frobenius. Okay, and then our torus T will be the fixed point of this Frobenius. Well, maybe let me call this. I don't know. What should I say? Maybe I should say that really T is this multiplicative group of the algebraic closure, and Tk, or maybe T of k, is the fixed point set of Frobenius acting on this. Maybe I should. Okay, then we have the dual algebraic torus. So before I denoted by this check the Pendragon dual group, but now I don't want Pendragon dual because this is some discrete group and its dual would be some compact group. I don't want compact, I want something of the same sort. Well, maybe I should say it this way. So this is just the multiplicative group of one copy of the algebraic closure, tensor, say, over Z by some lattice Zm. And this lattice Zm is canonically the lattice of homomorphisms from one-dimensional torus to T, so it's called co-character lattice. Okay, and now this way we associate tori to lattices. Okay, all the lattices are isomorphic, all the tori over algebraic closure are isomorphic, but still. Now, the co-character lattice is called this. And now, this can be dualized. From this lattice to Z, some dual lattice. Well, in fact, it's the character lattice. Okay. And it's denoted x upper star of T. Then to this dual lattice, we're going to associate some dual torus, namely T check is the same one-dimensional multiplicative group of the algebraic closure, turns out a dual lattice. Okay. So once again, as abstract groups, they're all the same, but for example, they're equipped with the action of some Frobenius automorphism, which may be non-standard one, and then it will give rise to the action of dual Frobenius automorphism here, which will be already not necessarily isomorphic. Okay, so there is a dual Frobenius action on the dual. Okay, and now, well, I hope you heard something about classification of semi-simple, simple Lie groups, yeah, in terms of root data. So, what, Chevalier classification. Reductive, but simple or semi-simple is good as well. So you start from some torus, and then there is also some combinatorial data. Well, it's called Ruby. Well, we just fix a root system, or a core root system. Are in the character lattice of T, and the core root system in the co-character lattice of T. Okay. Well, you need to know what it is, but maybe I'm not good at details. I presume that you do know what it is. And then this Langlands duality. Interchanges R and R check, and replaces your initial torus by dual. And then so it is some operation on the isomorphism types of reductive groups, and well, it happens so that indeed GLN dual is isomorphic to GLN, and maybe you've seen many times that SLN dual is isomorphic to PGLN, and SO to N dual is isomorphic to SO to N, and the SO to N plus 1 dual is isomorphic to SP to N, and so on and so forth. Say there are also spinor groups, the double covers of those, and the spinor group is of 2M is dual to the projective orthogonal group, and the spinor group of 2M plus 1 dual is projective symplectic. Okay. Yes. So. Well, very roughly, the irreducible characters of G over finite field well, in other words, you take G over the Lebesgue closure, and then take the fixed points of Frobenius, are numbered by conjugacy classes in a dual group, G check over the algebraic closure. Again, Frobenius fixed points. But it is really so for GLN, but again, I would say never never anymore. So it's false as stated for all the other groups, and this is some subtle point. Well, related to the fact that the nilpotent orbits are are not simply connected. Well, they're not even simply connected for GL2. There is nilpotent orbit, nilpotent cone without zero. Yeah, nilpotent matrices. The nilpotent cone is given by equation A squared equals BC. Yeah, and the orbit is that when they are not equal to 0. Okay, and then this is the puncture plane modulo plus minus 1. So it does have fundamental group plus minus 1, but it does not have non-ramified covers equivariant with respect to the action of GL2. So its equivariant fundamental group is trivial. And the same is true for arbitrary nilpotent orbit in GLN. But it's false for any other group. And because of this, because of those finite equivariant fundamental groups present for other groups, this is not literally true. There is some subtle, well, small discrepancy, very small discrepancy due to the existence of this fundamental group, non-trivial. Okay. But well, anyway, this is a sort of a baby version of Langland's reciprocity. And maybe let me say a few words about what is this. Well, maybe let me first say what is this Langland's reciprocity, namely the irreducible representations of such a group, G of K Frobenius fixed points over complex numbers. Should be more or less by ejection with homomorphisms from the Galois group of our field into the Langland's dual group. Now, this Galois group is essentially, well, Z, maybe Z hat, maybe, but it's generated by Frobenius. Again, homomorphisms up to conjugation, up to isomorphism. And so you just have to specify the image of this single generator, Frobenius. So just an element here, and we get conjugacy classes. Okay. So it's not quite true, as I just said. Maybe it is true for GLN, but not quite true in general. You need some extra parameters. These extra parameters are called L packets. So what is really true? Well, maybe L packets should be on this side. L packets here really do correspond to those homomorphs up to conjugation. But each L packet has something to do with the fundamental group of important ones. Okay. And now, well, let me say a couple of words about the adolescent version. Why there's a baby version of something else. Well, so it all starts with L functions. And these L packets are the same L as in L functions. And those go back to Dirichlet. And then Frobenius. Well, maybe Dedekind and Frobenius. Well, and many others, and so on. So you really can't quite stop. So maybe you heard that Dirichlet introduced some certain L functions to prove his theorem about prime numbers in arithmetic progressions, and then well, it was some modification of the Riemann zeta function, and then it was realized by Dirichlet himself and Dedekind especially that you could write similar expression given any character of Galois group of rational numbers, and then again it was realized by Dedekind that it was not somehow, for some arithmetic applications, it was not enough just to work with characters. I mean homomorphisms to abelian group to C star. If the Galois group of some extension was abelian, like for say cyclotomic extension that was used by Dirichlet originally, then it's fine. But if the Galois group was non-abelian, for example, if it was a simple group like A5 of 60 elements that has no characters at all, abelian characters, then it was not possible to write anything at all, but something was there. It was clear Dedekind, so he gave this problem to Frobenius to somehow invent a definition of L function in case of non-abelian extension. And then Frobenius eventually came up with notion of characters, and then having characters, he just plugged this into expression and gave definition of L function. So in the modern language, if I have some field extension, say K over Q, and say G is let's say Galois group of K over Q, and say sigma is a representation to GLV. So V is some complex space. Then the L function of sigma and parameter S, like the Riemann zeta function, is the product overall. Well, I don't know how. Prime ideals in the ring of integers. Okay. And then you take the inverse determinant, essentially the characteristic polynomial. But in this characteristic polynomial, you take as a parameter q to the power minus s. Now q is always, well, qp, so to say. QP is always the cardinality of the residue field, OK modulo P. And then you take sigma of Frobenius at this place, P. But Frobenius at this place, P, does not really make sense. Well, again, I assume that you do know something about basic number theory. Yeah, and then, well, the Galois group, the global Galois group maps into the product of local Galois groups, but in the local Galois groups, they have certain they have inertia subgroups, and the quotient model inertia subgroup is the Galois group of the corresponding finite field, so it's generated by Frobenius. But it's only in the quotient. If the inertia group acts trivially, and in any finite dimensional representation, for almost all primes, it does act trivially, then there is no problem. This is well defined. But in general, you must restrict this to the invariance of the inertia group at P. If your representation is trivial, well, there is nothing here, and you get just this product, and this is the Riemann zeta function. Okay.
This is not adult version. This is adolescent version.
Well, okay, let it be done. Well. So here we had a representation of Galois group, homomorphism to GLV. But the discovery of Robert Paul Langlands in 1967 was that the isomorphism classes of representations of Galois group like this into some reductive group over complex numbers should be in bijection with something else, and this something else is called automorphic representations of G, so it's dual group to this, over the Adel ring of Q. Of K. So just the product of all completions. Well, it's the product of all completions. K, P completions, well, harmonic representations, but irreducible. Okay, and automorphic means that they enter maybe some function space, I don't know, of the Adel group modular the principal Adel. Okay, and this is the somehow crucial point, because this Adel ring is some restricted product of the local completions, and the corresponding group will be also the restricted product of the local groups, and its representations will be just tensor products of various representations of those local things, and there will be too many of them. Somehow, the important restriction is that they enter in this space. So it's say for SL2, it's something like SL2R over SL2Z, and for arithmetic applications, it's very important that you quotient out by this. Again, if you just quotient out by the maximal complex subgroup SO2, you will get the Lobachevsky half plane, and then this quotient will be some sort of modular curve. So I mean, it has some arithmetic meaning. Okay, and this would be bijection, which is not established till nowadays. It's a very somehow important guideline, but still after almost 60 years, it is in this form it is far from established. Though some other versions are already proven. So the main characterization of this bijection under this bijection, the L function of representation of Galois group on this side should go to the L function of corresponding automorphic representation. It's I. Yes. Okay. And then again, I don't know if you heard anything like this before. No. Say automorphic representations, automorphic forms. Automorphic forms are, in this case, very close to so-called modular forms. And no? Pardon me? Who has a book? Bump. Daniel Bump. Oh, yes, many people have books. Yes, that's true. So pi can be well, you can associate to pi the invariance of the maximal compact group of this something like this, the product over P, and this will be a function, a modular function. On something like this. Lobachevsky plane over SL2Z. And fine. And then this is not just a modular function, but it is an eigenfunction over so-called Heike operators. And the eigenvalues of these maybe eigenvalues of operators should correspond to eigenvalues. So on phi should correspond to the eigenvalues of Hecke operators at P, so to say, should correspond to the eigenvalues of Frobenius in here. So then the L functions will match. Okay, so so you need some independent definition of L function on the automorphic side, and I will not give this definition. It's rather problematic in general. But in case when you do obtain some actual modular function, eigenfunction, then just the eigenvalues of Hecke operators should correspond to the eigenvalues of Frobenius in here, and that's the definition of Langlands would-be correspondence. So the main thing is to match the L functions. Okay, but by the way, the funny story about this that you also maybe heard is that the L functions from arithmetic point of view were studied by many people, and say in the first half of 20th century by Emil Artin. He was maybe one of the most famous arithmeticians, number theorist, and well, he studied a lot those L functions. In particular, there was a problem about their analytic continuation. They're always defined for big real part of S parameter, and it's absolutely unclear how to analytically extend them to arbitrary S values of S, maybe with a few poles. And there was this problem. On the other hand, Hecke, Erich Hecke, studied the L functions of modular forms. And there, the analytic continuation comes somehow for free, along with functional equation, just because of this modularity. The modularity is some action of SL2Z. This SL2Z is generated by translation and by the inversion, so to say. And the action of this inversion just immediately gives rise to the functional equation, just as for Riemann zeta function. The Riemann zeta function is obtained by some sort of Millian transform from theta, some sort of theta function, and this theta function is modular, and the action of this inversion in SL2Z gives rise to the functional equation on Riemann zeta function. This is the most standard way to prove the functional equation. Maybe going back to Riemann himself. Yes? Pardon me? So I gave no definition, and essentially I said nothing, and I didn't give a definition of L function of automorphic representations, so I essentially said nothing about this, and I will say nothing in this course. I only want to say that Erich Hecke was studying L functions here, and Emil Artin was studying the L functions there. But the funny thing was that they worked at the same Hamburg University in Germany up to 1936, I think, something like this, until Artin left to US. And they never talked to each other. So then it took like 30 more years for Langlands to realize that they were studying the same thing. But before Langlands realized this, people didn't understand that those two classes of L functions were just the same. And then it dawned on Langlands that these two classes are just the same. And this is his correspondence. Okay, but anyway, yes. Well, it's just in case G is SL2. I mean, then this space has something to do with that. It's not really true. Well, you have to consider the system of congruent subgroups here, and then you take the inverse system of those quotients, modular congruent subgroups, and then the inverse limit of this system is really this. That's what I want to say. Okay, but anyway, the point is that there is a bijection between representations of some group over some field, and on the other hand, representation of the Galois group of this field into the dual group over complex numbers. Okay, and then you see that this baby version is just an instance of such ideology. Okay, but bijection between representations of some group over some field or maybe Adel group should correspond to the representation of Galois group of this field into the Langlands dual. In this case over complex numbers, in this case over the same finite field, but something like this should be true. So this is just general Langlands ideology. It also makes some sense over local fields. You don't have to take the product over all local fields. Just for one local field also makes sense. And by the way, for local fields, this Langlands conjecture is proved. Also, there are various classes of fields, one of characteristic 0, one of finite characteristic. The situation in finite characteristic is much better than essentially it is proved for, so to say, functional case. But for global fields of algebraic numbers, it's far from being proved, and even from being formulated. There's no no complete formal statement for the number of fields. Okay, so now maybe it's time to say something formal and correct. So, yeah, we did introduce some notations and would-be classification of characters, but as I stressed last time, the problem is to introduce some integral structure in the would-be space of characters. And we did this. I mean, we introduced those Schur functions so that they form an integral base of the lattice of characters, but we don't know this yet. We'll have to prove this. So we need some control over the space of characters. We need to somehow produce the lattice of characters a priori, not knowing the characters in advance. And this is done via some nice trick relating modular representations and representations with complex coefficients. So we will prove some lemma about this. So we fix theta small theta, a character from the multiplicative group of the algebraic closure of our finite field into complex numbers, and G, an arbitrary finite group. Then we'll apply it to GLN of a finite field, but so far it's an arbitrary group. And then we have a representation rule from G to we have a representation over finite field. So into, well, we were studying characters of GLN, but as a tool, we first study representations into GLN over our finite field. So modular means a representation over finite field, so modular P. Okay. Now given an element in G, we denote by u1 of x and so on, un of x, the eigenvalues of rho of x. So they lie in a priori they lie in an. Okay, and now consider some symmetric function. With integral coefficients. And finally, chi is a function on G that sends x to this symmetric function of its of theta of eigenvalues, theta of u1 of x, and so on, theta over un of x. So the claim is that chi is an integral linear combination of characters of G. I mean, of complex characters. So this is the essential part of the claim. It's integral linear combination. I mean, certainly it's a central function, but the point is that the coefficients are integral. Okay. So we will not prove this lemma. I mean, we'll reduce it to some basic results in modular representation theory, but not prove some Brouwer theory. Brouwer theorem. So we'll make some reductions and reduce it to Brouwer theory. So first, it suffices to prove it for the basis, a basis in symmetric functions. For example, elementary symmetric functions, and then replacing by its exterior power suffices to prove for just E1 just the trace. Now, first consider the case when the order of G, let's call it G small, is prime to P, characteristic of K. Okay, so then Q is invertible. Modulo G. Q is P to some power, the cardinality of our basic field, ground field, invertible in Z modulo G. So that G divides Q to the power R minus 1, and R is just the Euler function. Phi of G. So now we will view our finite field or its degree and extension as the residue field of the ring of integers in the algebraic number field of roots of unity. And then we'll lift our representation into the finite field to the ring of integers of this algebraic field. So what do we have? The eigenvalues ui of x, they actually lie in MR this extension of our finite field, and we only need our character theta restricted to this MR. Okay, now MR is a cyclic group, and it's isomorphic to its dual, non-canonically, but somehow. And it suffices to check the lemma for a generator theta of this group. So if theta is theta not to some power, then consider f of t1 to the power s. So S, and again perform the same reductions. Okay. Now let O be the ring of integers of the algebraic field of roots of unity. Namely, we take the roots of unity of degree q to the power r minus 1. Okay. And P in O, the prime ideal containing P, our characteristic of our finite field. Okay, then the residue field O modulo P is isomorphic to Kr. It is a non-ramified prime. And well, by some basic Brouwer theory, our representation rho can be lifted to sigma from G to GL N O. So there is projection to GL N K. And there it is lifting. Okay. Now let U be the group of roots of unity in this ring of integers. And in fact, it's isomorphic to well, reducing modulo this prime ideal P. We get an isomorphism from U to the multiplicative group of Kr, Mr, and this theta naught is just the inverse isomorphism from Mr to U. Ой, привет, сейчас я приду. Через 15 минут приду. To U in the multiplicative group of O's in the multiplicative group of complex numbers. So we're almost done because we were interested in the trace, and we just take trace of this in there. But it means that trace goes to trace, right? Our symmetric function was just the sum of eigenvalues. The sum of eigenvalues is just trace, and that's the desired lift. So let Vi of x be the eigenvalues of sigma of x. They are the roots roots of unities or roots of unity of degree G. So Vi of x lies in U in this roots of unity, and Vi of x modulo or prime ideal is Ui of x, and hence chi of x is the sum of theta 0 of Ui of x is the sum of Vi of x, and it's just the trace of sigma of x. So we wanted to prove that our chi was linear combination of characters. Now it's just a character, just the character of this particular representation. Fine. So this was for the case when our group had an order prime to P, to our characteristic. Now for arbitrary, G, use the main theorem of Brouwer that a character, well, a function, central function chi lies in R of G. This is the integral combinations of characters if and only if its restriction to any elementary subgroup H in G lies in the similar space for an elementary subgroup. Now, elementary subgroup means that it is the product of a cyclic group, some order, Z modulo and Z times some L group. So now L is a prime, but distinct from, well, first of all, it's different from this. Yeah, just a prime different from that. A cyclic group and an L group for some different prime. We may say that H is the product of P and H prime. So P is a P group, and H is some order prime to P, and that's enough. I mean, for H prime, we've already H prime was covered by the first case, and P we will study now. So for an element in P, the eigenvalues of rho of y are all equal to 1. Yeah, because we're in the field of characteristic P. Yeah, there are no roots of unity of degree power of P except for unity itself. Y commutes with anything in H prime. So rho of y and rho of H prime can be well, simultaneously conjugated to upper triangular matrices. And they commute, so the eigenvalues of their product will be equal to the eigenvalues of A prime, which we already considered. Conjugate to upper triangular matrices over QR, hence the spectrum of y, no, of H prime equals the spectrum of y, H prime. So we know that chi restricted to H prime lies in R of H prime, and hence chi restricted to H lies in R of H, hence chi on G lies in R of G. Okay, so this lemma is proved. Well, now I do not know. I mean, we need again some notations. Maybe I only have 5 minutes, so maybe it makes no sense to introduce this notation. Maybe we'll start with this next Tuesday. And then next Tuesday we will actually find the integral lattice containing the characters. This R of Gn will be explicitly described as a next step. And then we will be essentially done. We'll only have to check that S lambdas will be described. Then we'll check that S lambda lies in this R of Gn. And we already know that they form an orthonormal base, and that's it. We'll just have to check that the value at 1 is positive. That's it. Then they do form characters, and we're done. Okay, in a couple of weeks we'll finish with this. So I remember the request about Steinberg representation. Maybe any other requests? Not yet. Local fields. Okay. Pardon me? Also local fields. So the. Oh, are you also for local fields? So everybody Chinese is for local fields. How about Russians?